Welcome everyone to our webinar today, Develop Media Solutions and Apps for the Latest Intel Processors. Our presenter is Jeff McAllister. Jeff is a Senior Technical Consulting Engineer for Intel's Visual Computing, Media, and OpenCL software tools. He's one of Intel's resident FFmpeg, Media SDK, and OpenCL experts. Jeff has authored many white papers and articles. Throughout Jeff's presentation, feel free to send in any questions you may have. In the text field, we've got a couple of our experts in the background who can answer your questions throughout the webinar. We should also have some time at the end of Jeff's presentation for some Q&A. We're recording the presentation, and we will send you an email with a link to the recording as well as the slides when it's ready and available for you. When he's done with the presentation, when we are done with the webinar, we'll have a short little survey. If you're able to fill that out for us, we would appreciate it. And now I'll turn the time over to Jeff.
Welcome, and thanks for attending our webinar on how to get great media performance with Intel processors and software. So one of the favorite parts of my job is to help engineers like you get started with our technology. And so I'm glad to be here today to tell you about some pretty amazing stuff. So Media SDK enabling software plus Intel Skylake architecture hardware provides a compelling combination of features and performance. So not long ago, HEVC seemed pretty far away. We all knew it was coming. It was interesting for quality improvements, but it was just too slow to be a feasible alternative to H.264. So since the amount of video processing is always increasing, it's hard enough to keep up at H.264 speeds. So taking a step back from H.264 performance was simply not an option. But now we've got a combination of the capabilities of the Skylake hardware plus Media SDK or Media Server Studio 2017, which it's Media Server Studio 2017 is a big step forward for Linux. Windows has been there for a while already. So we've got some amazing H.265 performance for you. H.264 is still slightly faster, but the distance between H.264 and H.265 has closed by a lot. So for many, this could mean that the door to HEVC development has opened. Real-time encodes, even at 4K resolutions, are no longer a futuristic dream. You can do it today. And in this webinar, I'll show you how to use Media SDK to enable HEVC transcode or encode with performance close to the lightning-fast acceleration you've come to expect from our hardware-accelerated H.264. So I'll start with the hardware to give an overview of the GenGraphics GPU architecture, which allows us amazing performance. And then I'll dive into how you can use Media SDK to enable your applications to use those hardware capabilities. So jumping into the hardware, Intel processors offer some really amazing media capabilities. So whether you're developing data center transcode, live streaming, computer vision, digital surveillance, video stitching, you name it, if your application processes video, then hardware acceleration of that video processing is very relevant. And some might say that the acceleration is disruptive. The hardware, the fixed function acceleration, may not be perfect for every case, but for an increasing number of scenarios, the performance and power benefits are large enough, they might just be game-changing. The picture on your screen now is the standard die shot for 6th generation core processors. The architecture is sometimes referred to as Skylake. The processors take many forms, so this may not match your environment exactly, but the main ideas about the architecture will be the same. So you'll recognize the 4 CPUs here, which are as amazing as ever. They have great general purpose performance and a large software ecosystem. But the benefits of the processor don't stop there. There's another side of the chip. So what we're focusing on today is the GPU side, the integrated graphics processor. So this model is a mid-range core processor with a relatively small GPU. So here on the screen, you can actually see some of the components in the GPU enough to count them. So there are these groups of 8 execution units. We've got 3 of them, so there are 24 execution units here. The highest end GPUs are actually 3 times bigger, so we get up to 72 of these EUs. And there's also a lot of fixed function goodness there, which we'll show a bit later. So what I'm trying to describe now is that we've entered a heterogeneous era. And by heterogeneous, I mean multiple types of architectures and instruction sets together on the same system. So here we've got multiple hardware types within the same processor. The GPU has a different programming model and instruction set. And it was designed as a solution to a different set of problems than the CPUs were designed for. But when you're developing for heterogeneous systems, you can combine the strengths of the different hardware types. And we've got other hardware types as well, not in this processor, but heterogeneous is definitely a strong story for Intel. Getting back to Gen Graphics, one of the main strengths is the specialized media capabilities. Now, you don't have to go very far to get them because they're all integrated in the same processor. You can see here that we have internal communication ring, and the processor graphics is it's a stop on the ring. It's that deeply integrated into the processor. It also shares the same memory hierarchy, which enables higher bandwidth and lower latency when using the CPU and GPU together. Funny thing, but the GPU is actually heterogeneous internally as well. So it has 2 types of compute hardware. The first is these general purpose compute units, the execution units, shown here in blue, and the second is the fixed function blocks, shown in red. And within the fixed function, there are groups of capabilities. One is this VD box, video box, which provides the codec capabilities, encode and decode. And then there's the video enhancement box, which has a lot of fixed function implementations of frame processing. So altogether, the Skylake Gen 9 GPUs offer some really amazing video processing performance at low powers. And some of the features newly enabled in this new generation, Gen 9, are a fully fixed function version of H.264, motion JPEG encode, and the main attraction for today, which is fast H.265. So got some numbers here to back up the claims. So what we're looking at here is if you've got 15 transcodes at 30 frames per second, that means that's at least 450 frames per second of capacity. So you could use that to process 7 streams at 60 FPS like we have here. You could do 3 at 120, and then when you look at 4K, 3840 by 2160, that's roughly 4 times the number of pixels. Well, it's exactly 4 times the number of pixels, but the frames per second is roughly 1/4 of what you would expect with encoding or transcoding 1920 by 1080. So we have ABC decode and HEVC decode here. ABC decode is used in the table because it's faster than HEVC decode. Both options are given to show what HEVC encode speed look like. the hardware is capable of running asynchronously. So unlike a CPU implementation, where generalizing to a single core and thread transcode, you could model the performance as decode time plus encode time. Here, decode for the next frame can happen while the current frame is still encoding on the GPU. So the AVC decode numbers can be considered an estimate of what you'd see if you're doing encode only. So one thing to note is, when reading a table like this, that the performance is highly dependent on the settings of the encoder. It's highly dependent on content. The intent here is not necessarily to show that you're guaranteed this performance, but to show it's possible. And to show that you really can get numbers like this, I want to pop over to look at actually running some tests. So here I'm running the sample multi-transcode, which is one of the samples that comes with MediaSDK. Now here you can specify the input file. So this is a H.264 input. I'm just taking the first 1,000 frames of Big Buck Blending. So obviously this is a very easy encode, and it's not intended to be representative of every possible thing you might throw at the encoder. And here we have output to H.265. And a couple other parameters. An important one is target usage, which says it's the highest performance mode. So the intent here is just to show how you can start checking the performance basically as soon as you get MediaSDK installed on your machine. So you're just running the command line here. You see it compute for a few seconds, and then here you've got 1,000 frames completing in roughly 4 seconds. So this single transcode is roughly 250 frames a second. It's not quite as fast as that 450 frames per second that was on the table yet. But I think this illustrates an important point about the hardware. That we'll see in some slides later the different number of fixed function hardware units in different SKUs, and that can affect performance, and then also you need to have enough work to keep those busy. So here I'm actually going to run with a parameter file. So this is a nice feature of this sample, which lets you specify some more complicated pipelines. So here what it's showing is we've got one input, and the output goes into a queue basically. And then we've got four encodes to H.265 that all they're basically the same output. So that it's here just to illustrate the performance capacity. So when we run with that one decode and four encodes, then we actually see quite a bit better performance. So putting all those through together, those four transcodes, each of, actually that was not the right one. Here we go. So running the four together, each with encoding 1,000 frames, it's only slightly longer than running that single transcode of 1,000 frames. So this is actually getting up towards the performance that you could see on the table. And just illustrating again that you'll get the best performance with providing more work to the hardware. So back to the architecture again. Wanted to provide a little bit of a decoder ring for some of the terminology that you might find around the Intel websites. So the first place to look to find out about the GPU on your machine is arc.intel.com. Now there you'll see names like HD Graphics, Iris Graphics, Iris Pro Graphics, and those refer to, to different levels of the GPU and different capabilities. It's also this kind of good, better, best idea. So everything starts with this single slice, and then more pieces are added. You'll see these compute units, the general purpose cores, execution units, and the slice actually has a lot of memory hierarchy that goes with those execution units as well. And then there's the fixed function, which is in the outside of the slice architecture, and EDRAM as well in some of the higher models. So you may see the processors referred to as a 4+2. That's 4 cores GT2. 2+3E is 2 cores GT3, which is 2 of these, as we'll see in the next diagram, and EDRAM. That EDRAM again being to provide an extra level of cache that can improve bandwidth between CPU and GPU. And then the biggest configurations, which is things like 4 CPUs, GT4 and EDRAM, which is kind of the best configuration for Iris Pro graphics. So just digging down a little bit deeper into the GT levels, we designed the GPUs like this to provide a scalable design for multiple price and power targets. The slice architecture allows for 1 to 3 of these slices, and so here you can see this as we had in the previous slide, GT2, GT3, GT4. And then you can also see how the unslice lays out as well, where with GT2 you get 1 of these VD boxes or MFX boxes, and 1 VE box or video quality engine, and with GT3 and GT4 you get another one. So then the importance of keeping both of them busy was illustrated with running the example code, which showed that with a single stream it can be challenging to keep all of the hardware busy, but as you add more streams to process, you actually get greater efficiency, and so you can actually start thinking in terms of not just processing one stream, but processing many at a time. So looking a little bit closer at the stuff in those slices, the fixed function implementation in VDBox has ENC and PAC. So the ENC is the motion search, which is also a macro block type, motion vectors and sometimes bitrate control. Then there's the PAC, which is kind of the end part of the encode, which is the bit packing and entropy coding. And then now we do have a path that doesn't even need to touch those EUs. So that can be beneficial because as you remember, the GPUs are heterogeneous inside. So the unsliced part can actually be active, powered on and working, while the EUs are idle and clocked down. So by keeping everything on the fixed function, you can either use less power or leave those EUs open for other processing. That other processing could be things like frame processing for filters, that kind of thing to improve quality, or it could be other tasks like computer vision type algorithms. I guess I'll briefly mention that video decoding is also there. If you are looking through our some of our documentation, sometimes it's called the bitstream decoder or BSD, and that's a little bit less complicated. It's just one black box, one basically a single unified operation. So the bitstream goes in, the uncompressed surface comes out, and it's all taken care of very quickly by the hardware. And then we also have frame processing in VEBox. It's wrapped by this video processing hardware acceleration layer. So if you look at a pipeline with something like vTune, you'll see VP-HAL instead of the individual VEBox functions. But VEBox can do a lot of nice things like deinterlacing or color space convergence, and so the hardware acceleration for those parts of the pipeline can be very important too. So now I've gone through an introduction of the hardware that you're accessing, but unlike CPU programming, where you write directly to the hardware, accessing the heterogeneous components is a bit more complex, and the additional layer of some SDKs is needed to actually allow developer access to those hardware benefits. So it's a little bit different than traditional CPU libraries or SDKs. With CPU only, you could just start with a familiar programming language like C or C++, use standard GCC, and just roll up your sleeves and get started. Program directly to the hardware. And the SDKs can just provide some additional abstractions, some ease of use, quicker path to solution. But for the heterogeneous capabilities, you have to go through a driver. The driver adds a lot more complexity. It changes frequently, including sometimes the interface. So it's really too low level to be practical. But as a practical answer, the SDK tools from Intel can sit on top of that driver and provide a more consistent interface and a higher level of abstraction to make programming more productive. And it's these tools that developers would use to unlock the capabilities of the other side of the chip. So as we covered in the previous section, the capabilities of that hardware can be pretty significant, and so if you look here at that 72 EU, that GT4 configuration, and it can be a pretty significant part of the overall architecture, the overall real estate of the chip. And certainly a lot of the total transistor count, a lot of the total capability is then there in the GPU, and so the accessing the other side of the processor is then very important to to really make full use of the hardware. So the main focus of this presentation is Media SDK to get you access to those codec capabilities. So now I'll go into a little bit more detail about what you could do as a developer to start accessing all that hardware goodness. So Media SDK is a high-level framework. So the programming model is that you're just providing parameters for initialization, and you're basically setting up three types of operations. So Media SDK just does three things. It's encode, decode, and VPP for frame processing. This initialization stage lets you supply parameters to the framework, and then the main loop. All the application does is specify how the pointers move between the stages. So the actual compute happens somewhere else. Now, OpenCL and Media SDK can be great together. The OpenCL can extend these pipelines and really allow you a fuller range of access. But these are important because quite often the main need is just to have a ready-to-use codec. So with Media SDK, you can you get a relatively easy-to-use, quick to program approach that gives you direct access to the highest hardware capabilities, the full range of those capabilities. So just looking at the codecs that are provided and the new components that you get in Skylake as enabled by Media SDK 2017 or Media SDK. So we now have a fully hardware accelerated HEVC, and so the big news is we've got the hardware acceleration that will give you some great performance. So some limitations to be aware of, though, are that the primary focus of Skylake and Media SDK 2017 is main profile. So 10-bit support is coming, but it's not fully enabled yet. Also, the motion search doesn't have the full range that is part of that HEVC spec. The Skylake generation is still using relatively limited AVC motion search. Now you can still get some quality improvements from the additional capabilities of HEVC, but it's just saying that this is a starting point, and it's good now. It's going to get better. And another thing to remember is that we have progressive encode support now. No interlaced HEVC quite yet. So this AVC encode now has, from a hardware perspective, that was the VD-ENC pathway. In Media SDK, we call it low power. And a few slides later, I'll show how you enable that. Also, Motion JPEG gets hardware acceleration. This is a subset of the JPEG general processing. It's baseline only, and some other small limitations. It isn't quite a drop-in replacement for libjpeg, but there may also be some uses for accelerated JPEG processing as well. Now there are a lot of great capabilities here. The main focus is the hardware implementation, so because you also see software here on the list. The hardware implementations are the main reason for Media SDK. Those are the versions we usually recommend. There is one very notable exception with the software HEVC plugins that I'll also cover a little bit later. So we also have a very rich set of frame processing operations. So that to enable some common use cases, you can use the fast frame composition for video wall, logo overlay, that kind of thing, and we've got accelerated deinterlace, accelerated resize, so a lot of goodness there. And then if you need an operation that isn't on this list, OpenCL is there to let you fill in your own custom filters as well. So just wanted to zero in on the part of media that Media SDK covers. So looking at the traditional transcode pipeline, container support, demuxing, audio, network transport protocols, parallelization across multiple processors, everything. That's all external to Media SDK. Media SDK has a laser focus on just the core of the pipeline, which is the video elementary stream processing. For the rest of the pipeline, you can use other frameworks. So FFmpeg and GStreamer are popular, but you can also integrate with your own infrastructure. And the reason for making the rest of the pipeline external is so it's so well done elsewhere. There's a lot of value we can add with video elementary stream processing because that's usually the main hotspot. Wanted to show timestamp handling because it's a frequently asked question, and it can also illustrate how the pipeline works. So the input starts with this container format. Demux is external. It's Media SDK basically assumes it's already happened, and you pass in the output of Demux. It enters decode as a input bit stream. We can process that input with arbitrary increments. It doesn't necessarily have to match frame boundaries. The output is made available after decode is done as a uncompressed surface. VPP has a surface in, surface out. Encode has a surface in and a bit stream out. So for timestamps, because the container part is considered external, the presentation timestamps basically just go through the pipeline untouched. There are some exceptions like frame rate conversion and deinterlace, but in general, those timestamps are just metadata, and so hopefully, though, they can illustrate the flow of data from bitstream to surface and back to bitstream through the pipeline. Also wanted to point out that one of the big secrets to high performance for HEVC and all the other codecs is to use the right memory type. So since the usual reason for using Media SDK is hardware acceleration, this means you want video memory. So every Media SDK component does accept both types, and it isn't necessarily wrong to use system memory. It can be a great starting point for integration, but just want to say that integration would be the first step, and then after that, you can do another pass and also switch to the right memory type to get an additional boost. Another option which can simplify things is opaque memory. So it's called opaque because Media SDK handles the allocations. So some limitations, though, are that the surfaces aren't accessible by the application, which is why it's called opaque. And so if your pipeline includes non-medius decay steps, an extra VPP opaque memory copy would be required. So you'd have to set up a VPP operation that has opaque in and system or video memory out to actually get access. So opaque is a great option if you've got relatively simple medius decay pipelines, but you'll probably want to use video memory as it gives you a lot more flexibility. So just wanted to quickly point out the basic structure of medius decay optimized application. So kind of like the slide before, one of the big first steps is to initialize a session. Then you do some queries based on those parameters, and actually allocate your surfaces. Then there's a main loop, and I'll show a little bit more about that later. At the end, because it's asynchronous and frames are buffered, there's a drain loop to get the last few frames, but then that's very similar to the other main loop. So it's usually not a big extra complication. Just wanted you to know that that's there. A quick introduction to how this would start. This shows some of the important aspects of medius decay programming. That you initialize a session. Basically, every medius decay operation outputs a status. You're usually looking for MFX error none. Here, this is showing initializing two sessions. The first one software, the next one hardware. In a real application, you'd probably use the MFX auto any or hardware any implementation. Probably trying to start with hardware first and then fall back to software if hardware isn't available. So from the programming interface perspective, everything's initialized with this MFX video param struct. Here you just fill in some of the basic parameters like the codec and the profile, things like resolution. Decode's even easier. Most of the parameters are read in from the stream header, and then maybe the only somewhat complicated bit is using extended parameter sets. So I want to mention this because it's pretty common now for new features to be implemented as extended parameter sets. So this approach allows MFX video param to stay the same size as medius decay features grow. So instead of changing the struct between versions, you just attach additional parameter buffers. So the basic pattern is to set up the buffer, initialize the whole thing to 0, give the buffer ID, which is identifying the type of parameter set, and then also set the size. And because everything is set to 0, you get the default. Then you just want to set everything that is not default, the parameters that you want to change. So just wanted to point out again that setting those parameters is often quite trivial. So for example, to enable this new VD-INC low power fully fixed function H.264 encode, all you have to do is set this low power mode to on. So that's it. Also wanted to mention that now we have 3 flavors of HEVC. So the new main attraction, I guess, is to look at the hardware accelerated HEVC that's available in the driver for. I mean, it's distributed with the graphics driver for Windows, it's automatically installed with Media Server Studio 2017. So then if you have the Skylake hardware underneath, it's active and ready to go. Now this is in addition to the previously available options, which are the software plugins for HEVC that are in the MSS Pro edition. So these work on a broader range of hardware and have a wider range of bit depth and color space coverage. So the full software version can work on processors without GPUs, such as Xeon E5s. They're not quite as fast as the full hardware version, but they can be a great option when more quality is needed. And all these flavors of HEVC appear as plugins in Media SDK. You differentiate them with a UID. In the samples, the Skylake driver full hardware accelerated version is set up as the default. So I just wanted to really quickly show in code what the interface you'd see as a developer. So here again, there's this initialize step. You would set up the video parameters, query for the surfaces required based on that, based on the parameters you just set up. Then you can initialize the stage and actually do your allocations. The main loop is a the stages are implemented as state machines. So you'll probably need to loop over the operations multiple times to go through the states. So the outputs indicate the action you need to take. Seeing an error doesn't necessarily mean there's something wrong with the program. It just means that something is required from the application, from the developer. So here with ENCODE, more input is required to process the frame if you see that output. So just looking at what that looks like in code, when you call ENCODE, you give it a surface. If you are draining, if there's no more input surfaces, you just pass a null pointer instead. And then there are probably multiple loops over ENCODE frame async. So you look at what you need to do when more data is requested, if the device is busy or other states. When it's done, when ENCODE frame async exits with NFX error none, then you can sync, and then the output of ENCODE is accessible to the application. So just to wrap up, there are only a few things that you'll need to keep in mind for any Media SDK application, and this applies to any codec, including the new H.265, but all the rest. So Media SDK is asynchronous, so you're standing on the shoulders of giants here, using a pre-implemented asynchronous framework to match the hardware. Each stage can have multiple frames in flight, so you'll have to the application will have to anticipate that some frames may be locked while the session is working on them, but that asynchronous nature allows a lot better performance. That it's session-based. The operations are pipelines. The default color format is NV12, and you'll want to minimize copies. Media SDK is designed internally to minimize copies, but with things like using the right surface type that matches your application, you can minimize internal copies as well. So when you're optimizing, you can kind of think of a really short list of heuristic checks. So as you are going past your first implementation, trying to increase speed, you can try to make sure to get everything into NV12 and reduce color conversions. Avoid frame copies by using things like the right or the matching video format, and running asynchronously is important. Also, make sure your application is basically staying out of the way. So this can mean possibly threading or possibly just making sure that the SDK is getting the most uninterrupted flow of new tasks that your application can provide. I also wanted to mention again that OpenCL is available, and it's a great combination to extend your pipelines. So MediaSDK provides optimized codecs and frame processing operations, but basically for everything else, all the ways you might want to extend those pipelines, you can use OpenCL to access more of those GPU capabilities. So that lets you use even more of what's there on the GPU. You can do things like add your own algorithms to improve quality or do custom frame processing, and you can keep your pipelines on the GPU. Also wanted to point out that vTune can be an excellent tool, and it can actually give a great view of the concurrency, the heterogeneity of what you're doing. So this is a nice slide to end with, because we can see here the concurrency, the CPU threads and the GPU work is all on the same timeline. Execution unit work is shown on the same timeline as the video encode and decode and the VE-box work as well. So the tool allows this kind of full processor view, which is what we hope you'll think of as your programming for Intel processors. So to wrap up, if we hope you're interested in getting MediaSDK or Media Server Studio, and so we've got some links that you can follow to download and to get more information, and more of them here as well. So this webinar will be available on the web. Previous webinars will also be available. We've got lots of samples and tutorials, and a helpful forum as well. So with that, I wanted to wrap up. Thanks for listening, and now I'll be glad to answer any questions you might have.
Great, thanks, Jeff. And in fact, if you could go back a slide to the resources in case people would like to write some of those down. They will be available on the slides that that'll be available online here probably within a week, but people still may like to write those down. We do have a little bit of time if there's any more questions. Appreciate Mark and Anna in the background who've been answering questions as they've been coming in. So if there's any questions that have gone unanswered that you would like to pose to Jeff, we have some time. Looking through here, looks like everything's been answered so far, so we'll just give a little bit more time if anyone has any other questions for Jeff. And yes, we did record the session, and it should be available probably within a week. We'll send out an email to everyone who registered where you can download that. There's a question asked, could you elaborate a bit on Linux support?
Sure. The pathway to use the hardware acceleration in Linux is Media Server Studio, and that covers Skylake and Broadwell. So 5th and 6th generation core, or Xeon V5 and V4. The primary supported OS is CentOS 7.2, but we also have a generic install. And so that means that we provide all the components that you would need to port to other distros. We can offer a little bit of guidance on how to do that, but the main distro that we're focusing on is CentOS 7.2.
All right, thanks. Do you have any plans implementing solutions for stream multiplexing?
So by this, I'm assuming working across multiple processors. So it's a great question, and I think it's possible with the SDK, but it isn't necessarily within the scope of the SDK. So your application can certainly divide the work across multiple processors. You can either work on multiple streams, different processors, and you schedule the work that way. You can divide the input stream into segments, or possibly just group pictures or GOPs, and send those to different processors. You could also work at a slice level if you're willing to do a little bit of header rewriting, and process slices separately across multiple processors. But
Okay.
but as far as I know, we don't have any plans to wrap that into the SDK. So it's still going to be up to your application to actually do that multiplexing.
Great. Can you compare the speed of video encoding optimized by AVX2 and the GPU?
Okay, so it can often be a big difference. So say you're just running with something like X264 compiled to use the AVX instruction set. It can often be a 5x or so difference. Now, another way to think of it is that it kind of changes the old rules with performance and quality trade-offs. So before, you could basically infinitely reduce quality to increase performance, but now you don't necessarily have to keep going down that quality degradation to boost the performance. You can offload to the GPU, and often the performance is, or the quality is pretty close to what you would get on the CPU, and even when it might be a little less, it's certainly not as bad as just continuing to cut the complexity of the encode to to try to meet performance targets.
Okay. Now there's on the forums where you ask questions on the forum, how are those monitored? How quickly would someone be able to get back or get an answer if they go to the forums if they have questions?
Well, we do have folks monitoring them. Now, of course, everyone has lots of other work too. So it's definitely best effort, and your questions are important. There isn't a hard and fast agreement that we would have to get back, say, within a day, but we do try to respond, and we also hope that the community can respond as well. So one of the purposes of the forum is to communicate with Intel, and another purpose is for the community to be able to share answers, and for the community to be able to help each other as well.
Okay. And we just have a couple more minutes if there's any last minute questions here. All right. Well, thank you everyone for joining us. Appreciate everyone's attendance. Hopefully you found some useful information. Thank you to Jeff for presenting, and for Anna and Mark in the background answering questions as they've come in. And we hope you'll be able to download and try these out and learn from the samples and tutorials that are available to everyone. So again, thank you everyone for joining us.
Thank you, everyone.